In this video, I'm going to describe the regression discontinuity research method. It's a method that's not widely used in criminology yet, although there are examples of its use, and it certainly is increasing in popularity. That's probably because this method allows for causal inferences that are very close to being as strong and internally valid as experimental designs with random assignment. And with regression discontinuity, we can overcome some of the challenges that are associated with using random assignment. So we're going to spend some time working through these slides, give you some background and a fundamental understanding of the method, its strengths, maybe a couple of its limitations. Then I encourage you to move directly to the next video, which will show you how to use data to do the statistical portion of regression discontinuity using real data. So I want to start by talking about just the basic design of regression discontinuity, and mostly with regard to how it differs from experimental designs with random assignment and other quasi-experimental designs. Now, looking at the basic design here, you can see that it is quite different than what we've seen in our prior research designs. Of course, with experimental designs with random assignment, we typically just have the latter portion of this figure where you have two groups that have been randomly assigned, one to receive the experimental stimulus, one to serve as the control group, and then we have a post-test observation and simply compare the means between the two groups to see if there's an experimental effect. Now, with regression discontinuity, we have some additional information that we need. Briefly, the O sub A symbol refers to an observation on an assignment variable. This is something I'll talk about throughout the rest of the slides and explain, but basically it's a variable that we measure before assigning groups. Then we determine a cutoff on that variable, ideally a continuous variable, and cases that are above that cutoff are in one of the groups, and cases that are below that cutoff are in the other group. Now, I'll explain these terms and how it's used throughout the slides, but I will mention that early on, and perhaps for a few slides, some of the description of this method is going to sound like it directly violates some of the good practices that we've been recommending throughout this course. There will be times when it seems like regression discontinuity purposefully creates selection bias. But what we'll see as we move forward is that we actually take advantage of that selection bias because we know with certainty what the source of that bias is, and that's what gives this regression discontinuity method so much inferential power. So that's the terminology, but we'll elaborate on what all of those terms mean as we move forward. Now, I want to start by talking about how is this method different than other methods that we've talked about before, and that will help us understand how the method works in general. As you know, the key to most experimental and quasi-experimental designs is trying to create two groups, a treatment and a control group, that are as equivalent as possible in the pre-treatment period. That's most easily accomplished with random assignment because that creates two groups that are equal in expectations, at least. And then quasi-experimental designs deal with the problem of not being able to randomly assign in a variety of ways. But most of the effort is directed toward trying to create two groups that are as equal as possible. Now, regression discontinuity does something quite different. It actually bases assignment on differences between the groups, and specifically on known differences between the groups. So as I mentioned, we have an assignment variable that we start with. It can be virtually anything, and we'll talk about that in a couple of slides, but often it's actually a pre-treatment measure observation of the outcome that we're interested in. The example I'm going to use throughout these slides is an anger management program that we might implement in prisons. So, of course, among violent offenders, perhaps we're concerned that they might have anger and violent impulses, and so part of their treatment could be to try to manage those impulses. Now, with an experimental design with random assignment, we would just randomly assign violent prisoners to either receive the treatment or not receive the treatment, and then, of course, follow up afterward and make a post-treatment observation of their levels of anger, and then compare the means on the two groups to see if they're significantly different. With regression discontinuity, instead, we would measure some variable in the pretreatment period. It could be virtually anything, but it is very often a pretreatment measure of the outcomes. We might measure levels of anger before implementing the program. Then we use those pretreatment levels of anger to place the prisoners on a continuum from low to high levels of anger. Then we create a cut point somewhere in that distribution, and all of the people that have levels of anger below the cut point are assigned to the control group, and all of the prisoners that have scores on that pretreatment anger that are above that cut point are placed in the treatment group. Now, one advantage of that over using random assignment is that we can focus our resources and our efforts on this anger management program toward those that have the most need, because we would be using their pretreatment levels of anger to determine if they're in the program or not. And that's one of the reasons why we sometimes don't use random assignment, because it is somewhat inefficient by providing services or some sort of program to people who we may believe don't need it as much as others. Now, immediately, warning bells should be going off, because you should be thinking, well, but still, that sounds fine, but then when you measure those post-treatment outcomes, and you might observe, oh, well, the ones that were in the treatment group actually have higher levels of anger after the program than those that are in the control group, and that's specifically because you've placed the highest anger prisoners in the treatment group. Well, you'd be right. So if we just compared the means, that would be problematic. What we're going to find out, though, is we won't do that same method that experimental designs normally do. Again, experimental and quasi-experimental designs usually compare those post-test means. If there's a significant difference between the groups, then we assume that that's due to treatment, and of course, with some caveats about threats to internal validity. Those warning bells that should be going off tell you that, well, that would be problematic for regression discontinuity, because we would often expect those post-treatment means to be different. Perhaps there was some treatment effect that reduces the difference, but still, we've imposed some selection bias that could be very problematic for our causal inferences. Also, we might expect some regression to the mean. That's always a concern, even with random assignment, but in this case, it would be even more of a concern, because those cases that have the most extremely high levels of anger would be placed, of course, in that treatment group, because we've used that pretreatment anger as an assignment mechanism. And so we would expect some of those extreme cases to regress back toward the mean, which would look like a treatment effect, but could just be due to regression to the mean. So fortunately, regression discontinuity sidesteps all of those issues, because it doesn't compare post-test means between the two groups as a way to determine if there's an experimental effect or not. Instead, and I'm going to cover this graphically in the next couple slides, but instead what regression discontinuity does is constructs a regression, and that's of course the regression part of the name of the method. It constructs what is essentially just an ordinary least squares regression between the assignment variable and the outcome variable. So still the outcome variable, which in our case would be that post-test measurement of anger, that's the dependent variable. But instead of just looking at a difference of means, we look at a regression where we regress that outcome variable on the assignment variable. Then we look at the difference in the intercepts just before and just after the cutoff. Probably the best way to understand this is to compare it to interrupted time series. In that case, remember that we were looking at time, and so there was some pre-existing time trend or not, could have been a flat slope, but we're looking at change over time. And then we look at how that slope changes, how the predicted values change right at the point of intervention in time. And so one thing we look at is a level change, right? That was the last lecture we did. We look at that level or intercept change right at the point of intervention to see if there's a decline or an increase. Regression discontinuity is similar, except it's not looking at time as the predictor. Time is not on the x-axis. Instead, it's that assignment variable. And so right at the cutoff, if there's no treatment effect, we would expect no change in those predicted values. So there would be no level change right at that cutoff. If there is a treatment effect, then we should see that right at that cutoff, everyone that's above the cutoff on that assigning variable should be different, significantly different than those that are below. Sometimes we also look at the slope, just like in interrupted time series, we look at level changes, but also slope changes or trend changes. Sometimes we do that with regression discontinuity as well. Often there's not a strong expectation about the slope, but there could be, and so in that sense it is very much like interrupted time series. Now, if that's not entirely clear, hopefully we can clarify that a bit by looking at a figure. So imagine in the context of our example, we have our assignment variable on the x-axis, and that is pre-treatment levels of anger. On the y-axis, we have post-treatment levels of anger. Again, remember that the assignment variable can be just about any continuous variable, but we've chosen pre-treatment levels of anger, which is fairly common. Then we have a cutoff, and that cutoff can be set at various different places, but if there's no other good reason to choose a specific value, there are good reasons to choose them somewhere in the middle of the distribution, perhaps the mean or the median. But we have a cutoff that's been determined a priori. Every prisoner below the cutoff on pretreatment levels of anger have been placed in the control group, and all the prisoners that are above the cutoff value on pretreatment anger have been placed in the treatment group. So these are the highest anger prisoners before the program is implemented, and these are the ones with the lowest levels. Now, this particular figure shows what we might expect if there's no treatment effect. So we have a regression, essentially. It's a scatter plot, but we can include control variables if we like, but you can think of this as a regression coefficient or a slope. And we can see that, as expected, those with low levels of anger at the start of the program also tended to have lower levels of anger at the end of the program, and those with high levels before also had high levels after. What we're mostly concerned about, though, is what happens right at that cutoff. If there was a treatment effect, we might expect some decline for those that are above the cutoff, that are in the treatment group, and we would see a level change in that slope. Here we don't see that. We see essentially a regression continuity, no change at the cutoff. That would suggest no treatment effect. This next slide shows what we might expect if there was a fairly substantial treatment effect. Here, same setup, assignment variable on the x-axis, the outcome variable on the y-axis, and we see that for the control group, that regression showed a positive slope, where people with lower levels of anger initially still had lower levels, and then increased as pretreatment levels of anger increased. But right at that cutoff, we see that regression discontinuity, that level change, where the slope now shifts down. The slope doesn't seem to change, but there is a level change right at that cutoff. Still, as we might expect, even in the treatment group, people with higher levels of pre-treatment anger still had relatively high levels of post-treatment anger, but much lower than we would have expected if there was no treatment effect. If there was no treatment effect, we should see that slope, it continues to extend up to the higher distribution of the assignment variable, but that's not what we observe here. So again, think of this as interrupted time series, as if we were looking at a longitudinal series of data, and on the x-axis would be time, and at the point of intervention, whenever we implemented that program, we saw a sudden drop, a level change in the predicted values of the outcome. But here, rather than thinking of this as time, where time is not the assignment mechanism is some variable. And if that variable is an effective choice, then we can derive very strong causal inferences from this method. So you still might be wondering, but why does this work? So it just seems very strange to be imposing some sort of systematic bias by purposefully placing those with high levels of the pretreatment measure of the outcome into the treatment group. Well, let me review this again, because I think this is what's most critical in understanding regression discontinuity. In other experimental designs and quasi-experimental designs, the selection process is not fully known. With random assignment, we do know the selection process, its randomness. That's why we're so concerned about anything that might impact that randomness. But if it's truly random, then we know with certainty that the mechanism that was used to assign people to the treatment of the control group. In the absence of the ability to randomize, we use quasi-experimental designs, and we try to create two groups that are as equal as possible, but we don't know truly what that selection process is. We might allow people to select into groups and assume that they're selecting randomly, but we would have concern that there might be some other mechanism like motivation or desire to succeed that might be driving that assignment process. In regression discontinuity, that selection process is completely known and perfectly measured. Now, there are some caveats to that. So, for example, if we use the example we've been using of this prison program, if we measure pretreatment levels of anger and develop a cutoff, and then we truly, anyone who is at all below that cutoff goes into the control group, anyone who's at all above the cutoff goes into the treatment group, then we do completely know the mechanism that's been used for assignment. But there can be some problems, what's sometimes referred to as fuzzy regression discontinuity. For example, maybe at that cutoff, there are some close calls, and so whoever's administering this program might decide, well, this person is below the cutoff, but I know they could really benefit from this program. Or, yes, their anger levels were measured as relatively low, but I know that this is someone who is very violent from their past history, and so I'm going to move them into the treatment group. That would create some concerns about the internal validity of our findings and the statistical conclusion validity. We wouldn't have as strong of a finding because there was some fuzziness around that cutoff score. In other cases, it doesn't work so much for the prison example, but in other cases, this is often used in education research. In fact, it's probably where it's most common. And so you might have scores on a talented and gifted scale, and students who are talented and gifted may be assigned to a specific treatment. It's possible that, again, maybe teachers or administrators might shift someone into or out of the treatment and control group. It's also possible that parents might somehow try to influence that. They might separately have their children tested, or they might lobby heavily to the administration to have their child placed in one group or another. All of those sorts of potential influences on the assignment process are the main threat to internal validity, and I think we'll mention that again later. But we can still account for that. There are ways statistically to account for that, and I think both books discuss that possibility. But for the most part, even if there are some inconsistencies in assignment, we can still deal with that actually using instrumental variables, which I believe is the topic of the next lecture. But in most cases, as long as we are assigning carefully according to that assignment variable, then we know that selection process perfectly. So again, then there's rarely reason to believe, except for the exceptions that I just gave, that there would be some other reason that the cases just before and just after the cutoff are significantly different from one another. If we observe that strong regression discontinuity, we have a very strong reason to believe that that is due to the assignment, because it's unlikely that some other mechanism is so correlated with that assignment variable and it happened to produce a change right at the cutoff that we chose. So effectively, regression discontinuity uses the cases just before the cutoff to sort of predict what the outcome would have been for people just after the cutoff if there was no treatment, and vice versa. And that's how we can use the cutoff, the intercepts right at that cutoff, to determine if there's an experimental effect. Then the discontinuity part of the name of the methodology comes from that difference in those predicted values. Is there an abrupt change of discontinuity in that regression line derived from the coefficient? So just to review, again, we've got this regression line, and essentially what the method is doing is saying, well, what would we predict the values of the post-test score to be for the cases right after the cutoff if they hadn't been given the treatment? So that would be essentially extending that regression line upward. And then the same thing here. What if, predicting downward, essentially, what would we predict these cases just below the cutoff to be based on this regression line if there was no treatment effect? And then the difference right at that cutoff point, that level change or intercept change, is our evidence of a discontinuity, which would be evidence of a treatment effect. One other way I would look at this, and what gives you an idea of why regression discontinuity is very close to being as strong in terms of deriving causal inferences as experiments with random assignment, you can think of experiments with random assignment as a variation on the regression discontinuity method. Imagine that instead of using an assignment variable that is pretreatment levels of anger, instead we use a random number. So we just generate random numbers, which is easy to do in Stata or any other statistical application. We generate a variable that is just a distribution of random numbers. and we use that as the mechanism for assigning people to one group or another. If it's truly random numbers, then we should expect in the regression discontinuity framework a flat line with a lot of variability around that line, because that assignment variable would just be random. Then, if there is a treatment effect, everyone that's above whatever our cutoff is on that random number should have an abrupt level change. Now, not all of them, of course, will have the same levels afterward. There will still be variability around that regression line, but we should see a straight line before, and presumably with no slope change, a straight line after, but with that discontinuity between them. Again, the reason this would work is because we know the assignment mechanism. It just turns out that because we used a random variable as the assignment variable, the assignment mechanism is actually random assignment. Now, of course, it'd be much easier to just randomly assign them and not worry about regression discontinuity. But that also illustrates why we can just look at the difference of means before and after, difference of means for the treatment in the control group, because if it was an experiment with random assignment, then there would be no slope here. It would be a flat slope, and so we can just take the average of the cases in the treatment group and the average of the cases in the control group and compare them. With regression discontinuity, we're allowing for the possibility that there is a correlation between the assignment variable and the outcome variable. There isn't always, but there could be. In this case, we would expect there would be, because it's the same concept being measured. And so we're taking into account the fact that there might be some relationship between those two by, instead of using just a difference of means for the control and treatment group, instead modeling that as a regression line and looking at the abrupt change at the cutoff. Okay, now let's talk a little bit about how do we choose an assignment variable. Turns out, like I've said, it's very easy. You can use just about any variable. It can be the same measure as the post-test measure, as we've just described, and that's probably the most common choice, because that gives us the advantage of having a pre-test measure to see not only was there a change between the two groups, a difference between the groups, but how much did they change, and maybe how much did certain types of people change. But it doesn't have to be. It can be a different variable. It can be a variable that's correlated with the outcome or not. We've seen that already. If you're using a variable that's the same as the post-treatment outcome measure, then it's probably going to have a correlation, but that's fine as long as we just model that accordingly using our multivariate regression methods. It can be a composite index. This is an advantage too, because maybe we want to combine multiple measures of some variable. Maybe we don't have access to information about a pre-test measure of the post-test outcome, but we can use a number of different variables to combine them into an index or a scale. That's not uncommon either. The main restrictions are it can't be something that's caused by the treatment. Now, this would be very unusual in criminology, and it's hard to imagine an example. But if there's anything that, any kind of variable that's caused by the treatment, then we can't use that as the assignment mechanism, because that would impose threats to internal validity. What looks like an effect of the experimental stimulus is actually being caused by the outcome itself, because it's being used as the assignment mechanism to place people into the control or the treatment group. It's not impossible to imagine, because sometimes we're using existing data, and well, even then it's still hard for me to imagine in criminology how we would have an example of that, but maybe some of you can come up with an example. It also can't be dichotomous, and this should be fairly clear. Because we're trying to generate this regression, we want to have a pretty strong predictive power to determine, well, what would we expect the values of the outcome to be for people who are just above the cutoff and in the treatment group. What would we expect their outcome predicted value to be if they didn't receive the treatment or if the treatment didn't work? So you want as much power to predict that as you can. If you have a dichotomous variable, you just have two values on that assignment variable, and so you can't generate any kind of regression line. It would just be a line between 2 points. It can be ordinal, but ideally with a large number of values. What a large number is very unclear. So I've never seen anyone use an ordinal variable, at least not in criminological research, because we usually have access to plenty of continuous variables. And since it can be virtually any variable correlated with or not with the dependent variable, then why limit yourself to an ordinal variable? Second question might be, well, how do you select a cutoff score? Maybe based on need or merit. So those that are most in need of the program could be the ones that are assigned to the treatment group, and we can adjust our cutoff with knowledge of who's most in need. Sometimes politically defined thresholds. I don't mean politically in terms of kind of the oppositional sort of political environment we have, but just in a sense determined by authorities, determined by the legislature. If they have a particular value in mind that they're concerned about, then you might use that as the cutoff, or make sure that the cutoff captures people with those levels. Otherwise, though, absent any other guidance or needs with regard to who's going to receive the cutoff, who's going to receive the treatment, most often the average of the assignment variable is used. Maybe the median if there's some skewness to that variable. Extreme values can cause problems. Extreme meaning for the cutoff, not for the observations themselves. You don't want to go too far in one extreme or the other, largely because then you would be restricting the amount of information you have on one side of that cutoff or the other. Just like any regression line, there are concerns with influence. And so if you have very few cases on one side of the cutoff, then they tend to be more influential, and you have less power to determine whether there's a significant difference before and after the cutoff, because the cases after the cutoff are sparse. Generally speaking, modeling is more error prone with sparse data. So again, even if we're looking at not regression discontinuity, we talked about CCJ6740, how when you start kind of cross-classifying cases and controlling for cases and looking at interactions, you can start to create cells in your data that are very sparse or maybe unpopulated. And so the less information you have about those sort of combinations of characteristics, then the less statistical power you have to model that. Also, generally speaking, statistical power is greater with equal or nearly equal sizes for some of those reasons that I mentioned. One benefit of experimental designs with random assignment over regression discontinuity is that with random assignment, we're just looking at a difference of means. There aren't other variables involved. We're not taking away degrees of freedom. When we start to shift to a regression discontinuity framework, it carries many, if not most, of the benefits of experimental designs with random assignment, but it does have less statistical power because we are introducing this pretreatment variable that has variability around its mean. We have a cutoff score that could vary, and then we have variability in the outcome. And so statistical power declines if we don't have large groups on either side of that cutoff. So I've mentioned this several times, but I'll repeat it again. And Shadish, Cook, and Campbell state this very, very strongly. You can tell by reading through that chapter, they have a real affinity for this method, and probably rightly so, because it is nearly as strong in internal validity as a randomized experiment. Any plausible threat to internal validity would really have to argue, well, two things. One is the possibility that the assignment variable is that is caused by the outcome, but we've already established that that's an unusual, perhaps can't think of any examples of how that could exist in criminology. But the other plausible threat to internal validity would have to be something that can cause that discontinuity that corresponds precisely with the cut score. It's similar, again, to interrupted time series, where we've said, well, that one major threat, probably the number one threat to validity, is that something else happened at the same time as our intervention that then will look like it's caused by the intervention, but was actually caused by something else. Now, with an interrupted time series, you're often dealing with large units, maybe cities, states, maybe the entire country, and so we often have data that's not very detailed in terms of time units. So maybe you have annual units, yearly observations, and so a lot of other things could be happening within those units at that point in time when we're identifying the year of the intervention that we're applying. And so that's more of a threat with interrupted time series. With regression discontinuity, you're dealing with individual cases, aggregated in the regression framework, but you also have a very precise cut point where, again, if you don't have some of those threats of that fuzzy discontinuity where people are influencing whether they're in the group or not right at that cutoff, but as long as you don't have that concern, then you should have a very precise measurement of where that discontinuity is, as precise as you want to make it with your choice of an assignment variable. and there's no lagged effect like there would be in an interrupted time series. There's no sort of delayed onset or gradual onset effect. It should be very abrupt right at that cut score. And so any threat to internal validity would have to also operate right at that cut score on that variable, which can be virtually anything. So you could imagine that it's very implausible that you would find some variable that satisfies that definition of a threat. So what that means is all of those threats to internal validity, things like selection, because we are imposing selection perfectly and then modeling it. History, there aren't other things that are happening right at the cutoff. Maturation should be reduced as well because it wouldn't produce an effect right at that cutoff. So we reduce those threats drastically, just like with random assignment. Now there are some similar concerns, much like there are with random assignment, but they are very, very minimized. Attrition can be concerned if it's correlated with the assignment variable, so that's an example of what I just said. We had said even with random assignment, if being in the treatment group, receiving whatever the treatment is, yields greater attrition among the treatment group, well then that's correlated with the assignment to the treatment group, and there's not a lot we can do about that, but it's no greater threat with regression discontinuity than it is with random assignment because it is just related to the treatment itself. There you might try to adjust the treatment, maybe have different dosage levels in terms of how many classes do they have to go to, how long do they have to attend the classes, do they have to do extra work outside of class. You can adapt your treatment itself. You can adapt the research method to take into account varying levels of treatment to be able to maybe evaluate or avoid concerns with attrition. Probably the biggest concern that's remaining with regression discontinuity that is unique to regression discontinuity and is not does not cause problems with random assignment is statistical conclusion validity. Fortunately, there are some ways we can evaluate and deal with this as well, but let me give you an example. The biggest concern is with modeling the functional form of the relationship between the assignment variable and the outcome variable. So again, we're trying to model this relationship between pretreatment levels of the assignment variable and the outcome variable, and then any apparent discontinuity in the regression line between those two variables would be treated as a treatment effect. It's possible, though, that there is a nonlinear relationship between our assignment variable and the outcome variable, and that's what this is showing. This nonlinear effect, even if we didn't have any treatment here, there might be some nonlinear relationship between them that could happen near the cutoff. Here it appears that the cutoff score falls right between that change in the slope, that nonlinear change in the slope. But you can tell that's not necessarily caused by the program because we wouldn't see this sort of gradual increase before and a leveling off after. We wouldn't expect that, especially we wouldn't expect this nonlinear trend before the cutoff if the effect is truly due to the treatment. What this probably shows us is that there was just an existing nonlinear relationship between our assignment variable and the outcome that we would be identifying as a treatment effect if we didn't take into account the possibility of that nonlinear relationship. We can also, so what we would do is instead of just in our regression, instead of just regressing the outcome variable on that assignment variable, we can model that assignment mechanism as a nonlinear relationship. So again, just drawing on what you already know from CCJ6740, we would just, in our regression, for example, add a squared term or perhaps a cubic term. It does complicate the analysis. It does reduce statistical power somewhat, so we would need even more, perhaps even more participants in our study to have the same statistical power, but we can model that and then still look at, given that nonlinear relationship between the two, is there an abrupt change at the cutoff? The way we can do that is by using interaction terms. And so we would look at the relationship between the assignment mechanism and this nonlinear functional form with the cutoff, and that would also allow us to do, and what this is demonstrating, it allows us to look at whether there's that slope change. So this is actually illustrating a different principle and a different concern with statistical conclusion validity, but one that we can certainly model. If we didn't allow for that slope change, then there would be what appears to be a nonlinear relationship between those two. But it's possible that if that slope change occurs right at the cutoff score, it's likely that that is due, we would expect that that's due to our experimental treatment. So if this were a regression discontinuity and we didn't take into account the possibility that there's a slope change, we might not observe this level change at the cutoff, or we might conclude that there is no level change, or there is even a level change, but we wouldn't observe that there's this post-treatment change in the slope. So much like an interrupted time series, we can create an interaction term between the assignment variable centered on the cutoff, just like we centered in the interaction for interrupted time series, centered the year variable on the year of intervention. We could center our assignment variable on the cutoff score, which if it's the mean, just mean center it, and create an interaction between that and the treatment variable to see if there is a difference in the pre-treatment and post-treatment slopes, while also looking at a difference in the levels at the cutoff. And then finally, we can have sort of a combination of the two, which is what I started describing. We can have nonlinear functional forms that are different before and after the cutoff score, while also observing this level change. This becomes much more complicated, though, because due to these nonlinear effects, you'd have to have probably at least a squared term for the assignment mechanism. And then you'd have to have an interaction between the cutoff score, be the before and after the cutoff, a dummy variable for that, much like our pre and post intervention variable for interrupted time series. You'd have to have that interacting with not just the assignment variable, but also the squared assignment variable. And that allows for different functional forms for the sort of before and after the cutoff, or in other words, for the control and the treatment group. That is a much more complicated setup. It just adds some additional interpretation, but it's certainly very doable. We also have the concern I've mentioned already, but I guess we'll go through it again, this idea between fuzzy and sharp regression discontinuity. The concern here is that the cutoff may not perfectly predict treatment near the cutoff due to some of the reasons that I mentioned, so non-compliance. This is one that I didn't mention, but you might be assigned to the treatment group based on your assignment score being above the cutoff, but if you are allowed to choose not to comply, then you're not part of the treatment group. Now, that's something that maybe that's not possible, especially in the prison example. Maybe that person wouldn't be included in the analysis, but then that's problematic because it causes questions of external validity. So if there's possibility of non-compliance, then that introduces some problems, much like it would with experimental designs with random assignment. Participant influence, if they're allowed to influence the decision of being in the treatment of the control group. If administrators can, parents, for example, like I mentioned, then those are all concerned. So ultimately, what we are really measuring with the assignment variable is the intent to treat. This is something that becomes important for methodologists because of concerns about whether the assignment mechanism is truly reflected by simply the cutoff score, if there are other things involved. That's much like our concern with random assignment, where yes, there may be still differences, but we're really talking about equal in expectations. But here we're identifying essentially the intent to treat. But when these issues are minimized, noncompliance and so on, then the intent to treat becomes equivalent to actual treatment. So as long as you don't have many concerns with regard to these issues, then it's not as much of a concern. But the book will describe, and we'll talk a little bit about this method, well, extensively about this method in the next unit. You can use something called two-stage least squares with instrumental variables to identify the treatment effect. There are ways to use this notion of intent to treat with other sorts of assumptions that have to be met about the instrumental variables to be able to account for the possibility that you have this fuzzy discontinuity because of problems with the assignment mechanism. The last thing I'll say, and I've alluded to this a bit already, is that regression discontinuity, while it has many of the same strengths, nearly all of the same strengths as experiments with random assignment, it does have less strength in its statistical conclusion validity. So essentially trying to identify a significant level change and maybe a significant slope change at the cutoff can be difficult because you need more statistical power, which usually means you need a larger sample size. And so prior research using these Monte Carlo simulations, where you simulate things thousands and thousands, hundreds of thousands of times with changing various parameters of the data, these studies show that you need about a little less than 3 times the sample size for a regression discontinuity to see the same, to be able to detect that effect the same as you would with just experimental design with random assignment. So that just means you will need a larger sample size and then choose a correct, appropriate cutoff that creates some balance between the treatment and control, the size of the treatment and the control groups. So modeling, I've already alluded to this some too, but just to kind of summarize, the modeling is based on just a standard OLS model. And it's even more simple than interrupted time series because we don't have to worry about autocorrelation because this is not temporal data. So in many ways, and really in most ways, the statistical method for assessing this level and maybe a slope change at the cutoff score is very similar, almost identical to how we tested statistically interrupted time series, but in somewhat simpler ways because we're not worried about time. So again, we use the assignment score as the key, one of the key independent variables. We center it at the cutoff value, and that's because we're going to create this interaction that allows us to show, is there a level change at the cutoff? So we'll center the independent variable, the assignment score, on its cutoff value, which is often the mean, in which case we would simply mean center, so a value of 0. Either way, a value of 0 reflects whatever the cutoff score was on your assignment variable. So you include that, and that's how we create the regression line that we're going to examine for discontinuity. We also include a dummy variable that identifies the treatment and the control cases. So just a dummy variable where usually 1 is the cases that are in the treatment group and 0 reflects cases that are in the control group. Then the key thing is we include a multiplicative term to test for the difference of slopes. So we create an interaction variable between the assignment score centered at the cutoff and the dummy variable identifying treatment and control groups. So essentially in interrupted time series, the assignment score was the year variable. The dummy variable identified treatment and control cases was just whether it was a pre or post intervention time year. And then we created a multiplicative term that was an interaction term between those two variables. And we centered time on the year of the intervention. Here we're centering it on the cutoff score. So very, very similar to interrupted time series. Then, like I said, if you are concerned that the assignment variable is non-linearly related to the outcome, then you can include a squared term or maybe multiple squared terms to capture that functional form. If you have those squared terms, you also need to include interaction with the squared terms to be able to model precisely the changes, the nature of the slope before and after, the functional form of the slope before and after the cutoff for the treatment group versus the control group. All right, just a few words on some other good practices that can be followed. These are these sort of design elements that we can include to enhance our confidence in our causal inferences. First, and these will be somewhat similar to the recommendations for interrupted time series as well. First, we can re-estimate the models using an outcome that should not be affected. So just to, if we find what looks like a significant discontinuity in the outcome at that cutoff score, that seems like very strong evidence of a causal effect. But if we can then demonstrate that for another variable, maybe one that's kind of a similar sort of variable, but not correlated with the outcome, that shouldn't have been affected by the treatment, if we can demonstrate that there's no such continuity for that variable, then that enhances our confidence in the causal inference. We can also re-estimate the models using arbitrary cutoffs, using a cutoff that was not the cutoff used to assign people to treatment or control. Certainly, we would not expect there to be a significant level change at any other cutoff value, and so we can model that by using just false cutoffs. We can also re-estimate the models using a related but untreated sample of participants. Maybe there's another sample perhaps at the same prison that just wasn't eligible, maybe in a different cell block or something. And so those cases weren't treated, but they can still have higher or lower levels on whatever the assignment variable is. And in those cases, we shouldn't see any kind of regression discontinuity at the cutoff because they weren't treated. Also, when we're modeling interactions and nonlinearity, when you're trying to get at the functional form of that of the slope before and after, the recommendation is to overfit that model. So if you're concerned that it might be a functional form that's not just one change in direction, but maybe more, then certainly include that cubic term. You lose relatively little statistical power, and certainly the gains of correctly modeling the functional form of the relationship between the assignment variable and the outcome, the gains that you make by modeling that correctly greatly outweigh any losses in statistical